Okay, welcome everybody to the second part of this course on the foundations of quantum mechanics. Now, the thing I want to talk about next is quantum measurement and what's called the quantum measurement problem. So I have already this morning discussed some aspects of quantum measurements from the point of view of Bohmian mechanics. And already at this point, some issues came up that can be problematical. So let me now focus on that and talk in more detail about what the problem is about that and why that is a problem. So here, the basic approach is that we treat the apparatus that carries out the quantum measurement.
Ich muss mal kurz hier das andere Ding leise machen.
Any question? No.
You are not muted.
Okay, no problem. To treat the apparatus as a quantum mechanical system itself. After all, the apparatus consists of electrons and nuclei, and the nuclei consist of quarks. So it should be possible to treat it like a quantum system just for a large number of particles. So now the wave function of the apparatus, that would be a function phi on R3n, and n now is a large number, like 10 to the 23, or maybe larger. So if we do treat the apparatus like that, then we would have a composite system consisting of the apparatus on the object, big wave function, capital psi here. T0 is again the time at which the measurement starts. So at the beginning, we have a product state. Now that will evolve according to the Schrödinger equation. It will not remain a product state because of the interaction between the apparatus and the object. And typically it will evolve into this kind of superposition of macroscopically different states. Here, capital psi alpha is a wave function of the composite thing of apparatus and object, in which the needle of the apparatus points to the value alpha. So it's a superposition of different outcomes. So that means that the wave function of the whole thing at time t1 doesn't say what the actual outcome is. Okay, so here we see a problem coming up, shining through. We might have expected a state at time t1 with a unique needle position. And we might have expected a random state because the outcome of the experiment should be random. It should have a distribution according to the Born rule. Okay, so that's kind of the essence of what the problem is here. That's closely related to Schrödinger's cat. So Schrödinger's cat example is essentially just a variant of the same problem, of the quantum measurement problem, a particular version of the problem. Here, instead of a needle, you have a cat that could be dead or alive, depending on the outcome of a particular quantum experiment, decay of a radioactive atom within a given time span. It's sometimes called Schrödinger's cat paradox, but Schrödinger didn't actually mean it as a paradox, as opposed, for example, to Wheeler, when I discussed Wheeler's delayed choice experiment. Wheeler's understanding of it was it's a kind of paradox. It feels crazy, but that's the way it is. So for Schrödinger, Schrödinger's cat was not a paradox. It was an argument. It was an argument showing that there's something wrong with the orthodox or the Copenhagen interpretation of quantum mechanics. Okay, now Schrödinger's version aside, let's go deeper into the measurement problem. Okay, what exactly is actually the problem? So you may think, and in this little dialogue here, Bob gives words to that. Well, if the wave function, capital psi at time t1, is a superposition or not, it's not an unreasonable wave function because it still yields the right probabilities. When you ask what's the probability of the needle pointing to this particular value, you take the part of the wave function corresponding to the needle pointing there, you compute its norm squared, you get the right probability. So what's the problem? Okay, so Alice gives a response. Everybody agrees about about what the right probabilities are. Okay, so that is not the problem. Okay, then where is the problem? The problem is about what is there in reality. Now, Bob thinks of reality. What hell? I believe there is no microscopic reality. I believe that observables don't have values before the measurement. Now, Alice says, yes, but that's a hypothesis about reality too. You could assume that the reality on the fundamental level, at least for microscopic systems or something, consists just of the wave function and not any further things such as Bohm's particles. But nevertheless, that's a hypothesis too about what the reality is. It's not possible to say there is no reality. That wouldn't make any sense. It's a bit like in the movie The Matrix. That was the title of a movie that was in theaters maybe 20 years ago. And according to the story of that movie, everything you normally see is an illusion. It's a computer simulation that is fed into your brain by some evil scientists, and actually the room you're sitting in doesn't really exist. It's all part of the simulation. The other people you see, it's all part of the simulation. It's just a computer simulation. And then in some scene of the movie, you see what the reality actually looks like. So this underlines that even if you have the idea that everything that we normally take for granted, there are tables and chairs and trees and rocks, even if all that is incorrect, even if that is not real, even if that is just an illusion, then something else is real instead, maybe the supercomputer that does this simulation. Okay, now you could come up with different hypotheses about reality. Let's say Bohm has one hypothesis, other people may have other hypotheses. Okay. Now, the measurement problem puts constraints on the possible hypotheses. So some hypotheses will run into a contradiction about reality. So what are these constraints? Let me try to pin down exactly where the problem is. I'm saying here that there are three assumptions that together give you the problem. Here are the three assumptions. Number one, in each run of the experiment, there is a unique outcome. Okay, you would normally assume that if you do the experiment, you get an outcome, and then there's a fact about what the outcome is. Assumption number two, the wave function is a complete description of the system's physical state in reality. What does that mean? Remember Bohmian mechanics. In Bohmian mechanics, a description of the state of what is there in physical reality is to specify the wave function and the positions of all particles. Because according to Bohm, there are two things there in reality, the wave function and the particles. So if you want to specify the complete state, the complete physical situation, then in addition to saying what the wave function is, you also have to say what the positions of all the particles are. Okay, now this assumption two is a statement that is false in Bohmian mechanics, but we will explore what follows if we assume it. Okay, so the assumption here is there are no further variables such as particle positions. Once you have specified the wave function of a system, you've specified all there is in reality. You've specified all that nature knows about that system. Okay, that's an assumption. Assumption number three, the time evolution of the wave function of an isolated system, not entangled with the outside, is always given by the Schrödinger equation. It's unitary, it's linear. Okay, that could be wrong, of course. For example, it's conceivable that the correct equation perhaps is nonlinear, and that the Schrödinger equation is just an approximation, a linear approximation to a truly nonlinear equation. Okay, actually, we will see um, some example later in this lecture of a theory that denies this assumption. The GRW theory proposes that the correct time evolution law for the wave function is a stochastic law, a stochastic and nonlinear law, for which the Schrödinger equation is just an approximation that is a good approximation under certain circumstances, and a bad approximation under other circumstances, such as the circumstances that, that prevail in a measurement situation. Okay, now the claim is that together these three assumptions lead to a contradiction. Here's how. By assumption 3, the wave function at time t1 at the end of the experiment is a superposition of the psi alphas corresponding to different outcomes. In order to arrive at the statement that, that it's this superposition, we needed that the time evolution was linear. If the time evolution is not linear, then maybe it's not true that you get this superposition. Okay, so we use assumption 3 to get to this superposition. Okay, now in the superposition, that doesn't say what the actual outcome is. So psi of t1 doesn't select an outcome. Now, if there were further variables, such as Bohm's particle position, they could select an outcome. But by assumption 2, there are no further variables. So the only thing that's there in reality is the wave function, or something equivalent to it. Okay, so that means there is no unique outcome, and that contradicts assumption 1. Okay, so the obvious consequence of this reasoning is that we need to drop one of the three assumptions. Now, actually, different theories make different proposals for which assumption to drop. For example, Bohmian mechanics drops assumption 2. The GRW collapse theory that I just mentioned drops assumption 3. The many worlds theory drops assumption 1. Now you might still think, okay, maybe there's some way out. Okay, so let me discuss some suggestions that people have made for why this problem would not occur or how you could get around it. Okay, so let me phrase this again as a kind of dialogue where Bob describes certain suggestions for ways out or reasons why you might think that there is no problem. And then Alice gives an answer for about why this suggestion is actually not convincing. Okay, Bob, as a consequence of decoherence, it is impossible for a second apparatus to distinguish between the superposition and a mixture with frequencies given by the C alpha modulus squared. Let me explain that a bit. Okay. If you have a superposition, a system in a superposition, think of the double slit experiment, okay, where you have a superposition of a wave packet through the left slit and a wave packet through the right slit. And you want to prove that both packets are there. Okay, so what you do is you make them overlap and then they interfere. You see an interference pattern, you've proved that both packets are there. Now, when you have a superposition of macroscopically different packets, as the psi alphas, then it becomes very, very difficult to make them overlap and very, very difficult to make them interfere. So practically, it's impossible. So then it becomes practically impossible to prove that both packets are there. It becomes practically indistinguishable for an observer outside of the system, consisting of object and apparatus, a super observer with a super apparatus making measurements on this big system of 10 to the 23 particles, to distinguish between a true superposition and just a mixture. A mixture would mean, oh, sometimes it's this, sometimes it's that. Sometimes it's psi alpha 1, sometimes it's psi alpha 2, and it occurs with certain frequencies. Now, the situation with sometimes psi alpha 1 and sometimes psi alpha 2, that's what we would love to have, because it would mean, oh, sometimes the pointer points here, sometimes the pointer points there. That's what we want. But what we got instead from the Schrödinger equation was the superposition. Okay, so now Bob is saying, look, you can't distinguish anyway between the superposition and this mixture. Okay, now Alice replies, yes, that's true. You can't distinguish. But the question is whether in reality there is a superposition or a mixture. We're asking a question about what is actually there in reality. Is it a superposition or a mixture or something else? If it is a superposition, then it's not a mixture, and then we have a problem. Okay, next consideration. Bob says, nobody can actually solve the Schrödinger equation for 10 to the 23 interacting particles. It's just mathematically too hard. So what are you talking about, solving the Schrödinger equation for this kind of measurement operation? But Alice replies, well, we don't need to. It's true, we can't in practice do a computation of this wave function. But we know from the simple fact that the Schrödinger equation is linear that if psi alpha looks like a state including a needle pointing to alpha, then psi t0 evolves to the psi t1 that is a superposition of macroscopically different states. It's just linearity implies it, even if you don't know in detail which functions the psi alphas are. Next consideration, Bob says, systems in reality are never isolated. So the system that's relevant here would be object and apparatus together. Okay, in this consideration, I treated it in an isolated system, as an isolated system. Okay, I solved the Schrödinger equation for both together. And now Bob says, look, this is not realistic. How can you treat it as an isolated system? Okay, it's true. It's not really isolated, but basically, if you can't do it for isolated systems, then yeah, there's basically no hope how you could get the measurement right for non-isolated systems. Here's why. The way to treat a non-isolated system is by regarding it as a subsystem of a bigger isolated system. For example, the entire universe. The entire universe would be an isolated system. Okay, so maybe instead of taking the Y system to be just the apparatus, take it to be the entire rest of the universe. Okay, then you're stuck with the same problem. Bob says, oh, wait, are you talking about a wave function of the universe? Maybe there is no wave function of the universe. Alice responds, well, you're welcome to propose hypotheses about what there is in reality. Okay, but now the question is, can you satisfy all assumptions 1, 2, 3 together? And the claim is you can't have them because together they lead to a contradiction. I have some more of these. Okay, next one. Bob says, who knows whether the initial wave function is really a product, as in, oh, this should be psi t0. It's a typo on my slide, not psi t1, psi t0. So I assume that the initial wave function is a product of a wave function of the object and a wave function of the apparatus. Maybe that's not true, that it factorizes. Alice responds, well, if it's only approximately a product, it's not relevant whether it's exactly a product. If it's only approximately a product, then the problem persists. Okay, you can think about that. It's not a complicated consideration. Okay, here's Bob's next consideration. The collapse of the wave function resembles the collapse of a probability distribution. Here's how probability distributions collapse. As soon as I have more information, such as that my random variable lies in a particular set B, I have to update my probability distribution for X accordingly. That is, I take my probability distribution for my unknown quantity x, and then I cut it off outside of the set B, and I keep it only in the set B, and maybe I have to multiply by some normalizing constant. So here on my slide, I forgot the normalizing constant. Okay, so also probability distributions, they kind of collapse as soon as I do some measurement, as soon as I get some further information. So collapse is also there in ordinary probability. Why is it suddenly a problem in quantum mechanics? Okay, it's striking that there's kind of this parallel between collapse in probability theory and collapse in quantum mechanics. However, if we insist that the wave function is complete, which means that there are no further variables, that it's a complete description of everything that's there in physical reality. That was our assumption 2. So if we insist on assumption 2, then there never is any new information, as there is nothing that we're ignorant of. In other words, suppose we know what the psi is, the wave function of the object, and suppose we know what the phi is, the ready state of the apparatus, then we still don't know what the outcome of the experiment will be. It will still be random, but we know all the facts if we assume that the wave function is the complete description of the physical state. For example, in Bohmian mechanics, where the wave function is not the complete description of the physical state, then there are still the particle positions, which still we don't know, even if we know what the wave functions are. And we could get further information about the particle positions through, reading off the position of the needle, okay? But if we insist there are no further variables, then there is no further randomness. Everything is deterministic. Okay, so to me, it seems that none of Bob's considerations removes the problem. So we're stuck with the problem, and the upshot of this discussion is we need to drop one of the 3 assumptions. The 3 assumptions, let me reiterate what the 3 assumptions were. So I go back to this previous slide. Assumption 1, there's always an outcome. There's a fact about what the outcome is. Assumption 2, the wave function is complete. Assumption 3, the time evolution is unitary. Okay. Now, people have discussed a lot about the measurement problem. One thing that's important for understanding the measurement problem, one thing that's important for understanding the problem is that the problem is about what is there in reality. So many people have argued that somehow the problem is not a problem, but have not paid enough attention to the question, what is there in reality? Okay, so now I will describe another theory, a theory that solves the measurement problem, a theory of quantum mechanics that is based on the idea of spontaneous collapse. It's based on the idea of changing the Schrödinger equation in such a way as to avoid the measurement problem. So here's the key idea of the Ghirardi-Rimini-Weber theory, often called GRW theory. The idea is that the Schrödinger equation is only an approximation valid for systems with few particles, say less than 10 to the 4, but not for macroscopic systems, say with 10 to the 23 particles or more. The true evolution, that's the idea here, the true evolution law for the wave function is nonlinear and stochastic. Stochastic means inherently random, and avoids superpositions, such as Schrödinger's cat, or such as this measurement wave function, the superposition of the psi alphas, of macroscopically different contributions. Put differently, in this theory, the idea is to regard the collapse of a wave function as a physical process governed by mathematical laws, and explicit equations for such mathematical laws were proposed by Ghirardi, Rimini, and Weber in 1986. The predictions of this theory deviate from the predictions of quantum mechanics. However, they deviate very, very slightly. So little, in fact, that at present no experimental test is possible. People are working on that. They're trying to come closer to an experiment that for which GRW theory would make a prediction that is different from the prediction of standard quantum mechanics. Okay, I'll explain in more detail what this theory says. So it proposes a stochastic evolution law for wave functions, for, if you wish, the wave function of the universe. Okay, the wave function that would, in Bohmian mechanics, or I'm not sure in the standard view, at least in Bohmian mechanics, would evolve unitarily. Of course, if the wave function of the universe deviates from the unitary evolution, then that also has consequences for wave functions of subsystems. Okay, so this evolution law, the way I will present it is designed for non-relativistic quantum mechanics of n particles. It's meant to replace the Schrödinger equation as a fundamental law of nature. It involves two new constants of nature. Lambda will be the collapse rate per particle, and sigma will be the collapse width. And Ghirardi, Rimini, and Weber have proposed approximate values for these constants. Of course, these constants would have to be determined through experiment. But of course, that would have to be an experiment that can distinguish between versions of the GRW theory for different values of these constants. And that would, in particular, be able to distinguish between the GRW theory and standard quantum mechanics. And I've already told you that this is practically hard to do. Okay, so at this stage, the constants are just proposed values, rough ideas of what kind of order of magnitude these constants could have. So the claim is that with these constants, the theory would kind of be a reasonably good approximation to standard quantum mechanics. So here's the definition of the stochastic evolution for the wave function. Psi evolves as if an observer outside of the universe made at random times with rate n times lambda quantum measurements of the position observable of a randomly selected particle with inaccuracy sigma. Now I'll give you equations for that, for what that means exactly. So rate n times lambda means that the probability of an event in the next dt seconds is n lambda times dt. Okay, so here the events that occur are collapses of the wave function. According to the usual rules of quantum mechanics, collapses occur when an observer makes a measurement. Okay, but now the claim of the theory is these collapses, at least some collapses, also occur spontaneously without any observer doing anything. Okay, I said it's as if an observer outside the universe did something, but that's just a verbal description of how the wave function changes. Okay, so the statement is that spontaneously at certain random times that occur with this rate n lambda, the wave function spontaneously changes, and here's how it changes. In between these collapse events, the wave function evolves according to the Schrödinger evolution. And at these collapse events, the wave function jumps. So you have a psi t minus. So capital T now is the random time at which this jump occurs. Psi t minus is the wave function just before the jump. Psi t plus, the wave function just after the jump. And here's the law for what the jump does. It multiplies the wave function by a Gaussian function. Here you see the Gaussian function. It has width sigma, and it has center q, and it applies only in one variable. You apply to a random particle number k. So q sub k is the position variable of particle number k, which is one of the variables in the psi function. The q is a constant, and so at time t, you multiply it by a narrow Gaussian. That is, like, you localize it in in one of the variables, in the position variable of the kth particle. And this value q is chosen randomly. And here's a formula for what the probability distribution of this random value is. The probability that the collapse center q lies in a particular volume element of three-dimensional space is the following. You take this expression here, the psi t plus, you take the norm squared of that, that's the probability density. In other words, you take the psi t minus the psi squared distribution and form the convolution with a Gaussian. What does that mean? Okay, so essentially it's more or less just the psi squared distribution, but there's a kind of a fine change, a little change. Actually, it's not strictly the psi square distribution, but it's this psi square distribution convolved with the Gaussian. Here, the star here, now we can't see it. Why can't we see it? Okay. Hey, can you go away? Oh, no. Okay, so there's the little star means convolution, which means you smear out the psi square distribution with a Gaussian. But since the Gaussian is very narrow anyway, the sigma has a very small value, 10 to the minus 7 meters. That's not a big change. It's just a little change. Okay. Okay, let me show you in a picture what this operation looks like after we've seen the formula. Let's see. So I can't go. Wait. Okay, now I can go to the next page. Okay, so here is what the GRW collapse looks like for a wave function. So here, before the collapse, that's the wave function, and that's the wave function after the collapse. Here, what I'm showing you is two axes of the configuration space. Here's one axis, here's another axis. You know that, of course, configuration space really has more axes. And I'm showing you, the real part of the wave function. Okay, so this is kind of an arbitrary function, and it's kind of complicated. Okay, after the collapse, it looks like this. It has been localized in one of the variables, in the variable along this axis. So that's the position of particle number k. Here, I've taken the position just in one dimension. In the cross section of this function, you see the Gaussian shape here. We've multiplied by a Gaussian of a certain width sigma. Here, this is more or less the width sigma. Here you see the Gaussian. We've multiplied it. We've taken this function, multiplied it in one variable by a Gaussian, and this is what it looks like afterwards. Okay, so it has become localized in one of the variables for one of the particles. And localized where? Okay, so here's the center of collapse. On this axis here at this point is the center of collapse. The center of collapse could have been somewhere else. It was chosen randomly, more or less with psi squared distribution. Okay. So the evolution of the wave function looks like this. In Hilbert space, it's a piecewise deterministic stochastic jump process. What does that mean? That means that psi t jumps at random times to random destinations in Hilbert space. Okay, so these jumps occur at random times. Why is it a random destination? That's because we multiply the wave function by a random function. Why is that? We multiply it by a Gaussian, and the position of the center of the Gaussian is random. Okay, so that's why the destination of the jump of the motion of psi t in Hilbert space is random. In between such two jumps, the wave function just evolves according to the Schrödinger equation. That is, it evolves in a deterministic way. That's why we call it piecewise deterministic. overall it's a stochastic evolution, but every continuous piece of it is actually deterministic, just follows the Schrödinger evolution. Okay, so these jumps we also call collapses because, okay, it is very similar to what you have in the usual rules of quantum mechanics as a collapse, like an inaccurate position measurement. The inaccuracy here is the width of the Gaussian, the sigma. Okay, now let me go back to a previous slide. Here I said the lambda, the collapse rate, is 10 to the minus 16 hertz. So if you translate that into how often do these collapses take place, that means for a single particle, there's one collapse every 100 million years. So that's the explanation why we don't see collapses, because for every particle that we study, a collapse occurs only once every 100 million years. Now, if you have more particles, that means collapses become proportionally more frequent. If you have 10 to the 4 particles, one collapse every 10,000 years. For 10 to the 23 particles, one collapse and every 10 to the minus 7 seconds. Okay, so if you have a macroscopic number of particles, then you have collapses going on all the time, okay, within a fraction of a second. Now, for this theory, you can prove a no signaling theorem. That is, you can prove that actually the probability distribution, if you have a space-like separated system, then nothing that you do on one side will actually allow you to influence the probabilities on the other side in such a way that you could transmit messages in this way. So there's no faster than light possibility of transmitting messages by means of these collapses. Now let me talk about how GRW theory solves the measurement problem. In outline, you already know. We're denying assumption 3, we're denying the unitary evolution. So what does that look like concretely? I will say it in terms of this diagram here that we've seen before. So here we talked about the measurement process. We talked about the situation in which a single particle, let me go back to the first slide. A single particle is in a superposition of two locations, two locations that are, let's say, farther apart than 10 to the minus 7 meters. So let's say they're 1 meter apart. Okay, now one of the two wave packets now couples to a detector. Okay, so we get this the superposition of states of particle and detector together. And now a collapse occurs. Now, for the particle, okay, so you know that a collapse occurs kind of on a random particle. So a collapse could occur on the one particle that is the object, or it could occur on one of those 10 to the 23 particles that form the detector. Now it's 10 to the 23 times more likely that it occurs on one of the particles of the detector. So let's assume that is what happens. Within 10 to the minus 7 seconds, a collapse occurs and it hits one of the detector particles. So what we do now, or what nature does now to the wave function, is it multiplies by a Gaussian function on this axis, on the appropriate axis of this detector particle, with a sigma. Let's say if sigma is perhaps large like this, so it's larger than this packet. Sigma is 10 to the minus 7 meters. So this is kind of, it's much larger than an atom, but it's small on the macroscopic scale. So let's assume for simplicity that sigma is larger than the size of this packet, but smaller, considerably smaller than the distance between these two packets along this axis. Okay, so if you multiply by a Gaussian along this axis, then that means that in a strip around this horizontal line of width sigma, you keep the wave function as it is, and outside the strip, you set it to 0. Recall this, this picture that I showed you of how the wave function gets localized on a particular strip. So now that happens here in this strip. Okay. So then of the two wave packets, one disappears and the other one remains. The wave function has collapsed. And then that determines what the outcome of the experiment is. So let me go back one slide here. At this point, there were two possibilities for where the collapse could be centered. You see, in a superposition of the needle pointing here and the needle pointing there, suppose the collapse hits one of the particles of the needle, then there's a certain chance that the collapse center would be over here, or a certain chance that the collapse center would be over there. So the collapse could favor this packet and basically erase that packet, or the other way around, could favor this packet and erase that packet. So the way I've drawn it here, it was the northeast packet that survived, and the southwest packet was set basically to 0. It was multiplied by a Gaussian. It's not exactly 0, but very, very close to 0. So the situation is that as soon as a collapse occurs for one particle in the apparatus, the whole superposition breaks down. Of these two wave packets, only one survives. And as a consequence of that, also for the test particle, the object, the wave function has collapsed. Now, for a macroscopic superposition, such as Schrödinger's cat, the collapse would occur within 10 to the minus 7 seconds. And that's how we solve the measurement problem. If a macroscopic superposition occurs, it remains only for a very short time, such as 10 to the minus 7 seconds. And that seems acceptable. After 10 to the minus 7 seconds, you have a fact about what the actual outcome of the experiment is. So the wave function then would collapse up to tails of the Gaussian to one of the macroscopically distinct wave packets, psi I. So for Schrödinger's cat, that would be either dead or alive. And the probability that it collapses to a particular packet is up to Gaussian tails, given by exactly the values prescribed by the Born rule. So that is why GRW theory agrees with the standard quantum prediction to an excellent degree of approximation. In principle, the predictions of GRW theory can differ from those of standard quantum mechanics. Here's a simple example. Suppose we set up a double slit experiment in which it takes the particle 300 million years to travel from the double slit to the detecting screen. What happens then? For one particle, on average, every 100 million years a collapse occurs. So if there's 300 million years of time, then that means there's a chance near 100% that a collapse occurs. And if the collapse occurs, then you have difficulty getting the interference. Okay, so then instead of, so in that situation, you wouldn't have an interference pattern anymore. Whereas in Bohmian mechanics, or according to standard quantum mechanics, you should have, if you could isolate the system for 300 million years, you would see an interference pattern. According to GRW, you would not. Okay, so that's an example where there's clearly different predictions. But this example also suggests that it's not so easy to test GRW against standard quantum mechanics because you don't have 300 million years to wait. Another prediction in which GRW differs from standard quantum mechanics is the following. With every collapse, there's some kind of increase of energy. That's basically because the collapse makes the wave function narrow in position space, which means that in momentum space, by the Heisenberg uncertainty relation, wave packets become wide. And if you make things wide, then there's a certain contribution with large momentum values. That means contributions with high energy. And if that happens again and again and again, every 10 to the minus 7 seconds for some particle, then there's some contribution, energy is going up. So GRW theory makes the prediction that actually the energy of isolated systems spontaneously increases. Now, if you had very small values of sigma, much smaller than 10 to the minus 7 meters, then this energy increase would be large, and it would be easy to see. It would be a large deviation from standard quantum mechanics, but 10 to the minus 7 meters is a value of sigma that is relatively large and makes the energy increase associated with collapse very small. And in fact, it's so small that over 10 to the 10 years, the age of the universe, you get a temperature increase of objects by, I don't know, some tiny fraction of a Kelvin. Okay, so that's why why GRW theory cannot be easily distinguished from quantum mechanics due to this spontaneous warming. Here's a diagram showing how these GRW theories are empirically adequate. Empirically adequate means they make the right predictions. They make the predictions that we actually see in experiment. Here are 3 different versions of the same diagram. Let's focus on the leftmost one. I've already said the predictions deviate very, very slightly from the quantum formalism. That is from the standard quantum mechanical rules. And in this diagram, the diagram shows the parameter plane. So there are 2 parameters, the constants of nature of GRW theory. There's the sigma and there's the lambda. These are the 2 axes. So, and here in this log-log plot, now every point in this plane corresponds to a different theory. You see, in GRW theory, these lambda and sigma, they're constants of nature. So now we're looking at different values for these constants of nature. They lead to different theories. Okay, so now in this parameter plane, in this parameter diagram, I've drawn 2 different regions, the and the per. Means the empirically refuted region. So if the value of sigma and lambda were over here, for example, then the GRW theory with these constants would lead to predictions that actually deviate some experiment that we have already done. The the philosophically unsatisfactory region, that is a region where the parameters for other reasons, where the theory doesn't do what we want it to do. It doesn't lead to collapse of macroscopic superpositions. For example, for this point here in the parameter plane, it may be the case that Schrödinger's cat takes 2 years to collapse from the superposition into either dead or live state. Okay, that's not what we want. We want that that the Schrödinger's cat goes into one or the other within a fraction of a second. That's why certain regions of the parameter plane are unsatisfactory. And between, or let me add the following. The empirically refuted region is growing over the years because there's more and more experiments, better experiments. So this borderline here of the region is moving over the years from the northwest to the southeast. And now in the middle, there's an island here, a white region on the map that we cannot exclude so far. And this island is shrinking. So at some point in the future, perhaps when experiments have improved sufficiently, then they will either have confirmed the prediction of GRW theory and refuted quantum mechanics, or they will have closed this island and then there is no version of GRW theory left that is both philosophically satisfactory and empirically viable. So then that would mean that GRW theory has been empirically refuted, but perhaps it's still possible to come up with some other version of a collapse theory. So for example, CSL stands for continuous spontaneous collapse. That's another collapse version due to Philip Pearl. You see it has kind of a larger island here, a larger wide region.
What is the difference between the two GRWs?
The difference is the primitive ontology. One is with a flash ontology, the other is with a so-called matter density ontology. And that is the next thing that I will explain to you what that is. But I think at this point we should have a short break